I'm back working on the Z80 computer project, and as you can see I'm adding some additional circuits to it. This particular circuit is a fairly important one. I mentioned when I started this project that I wanted the system to be compatible with something like CP/M. Now the only real function of CP/M is to allow files to be copied to and from floppy disks. It's kind of the mass storage control system. So trying to run CP/M without any mass storage would be fairly pointless and also quite difficult. So the next obvious step was what sort of mass storage would I use for this project, and you can probably tell already from what's on the bench that what I'm using, I'll just move the camera, is a floppy disk. And when I sat down and thought about what I wanted the system to support, what I came down to was I want the system to be able to support up to 2 floppy disk drives, and for those drives to be able to support single density, double density, single-sided and double-sided. So before we look at the circuit, I won't go into too much detail about the circuit itself in this video. If you want more information on this, then please leave a comment. But I thought I'd try and clear up some of the kind of mystery behind floppy drive systems. I see a lot of confusion about it online, and it's mostly down to the sheer number of different types of disk and the way they're formatted, etc. But the general concept is fairly straightforward. So if we look at a typical floppy disk layout, I've kind of strained it out here, but normally the disk is divided into tracks. These are obviously circular tracks around the disk. I've strained it out here, and each of the tracks is subdivided into sectors. So they're represented here by these little marks. Now each sector on a track is probably not necessarily what you'd expect it to be if you're not familiar with floppy drive systems. And each sector contains information such as this. This is a simplified sector, typical sector on a disk. But what's actually in these sectors depends on how you format the disk. There's nothing inherent about the sectoring on a floppy disk. Even the hard sector disks, where there's an index mark, a physical index mark for each sector, what's actually in the sector itself is entirely down to, well, you can write whatever you want on there when you format the disk. But there are fairly well established types of formatting that have been accepted and been around for a long time, but you can come up with your own if you prefer. Just bear in mind that most floppy drive control devices expect certain formatting to be adhered to. So what we get in each sector is not just the payload, and when you hear phrases about the size of a sector, 128 bytes, that sort of thing, that's only talking about the payload. But for example, if we use, this is currently set up for 128 byte sectors, but each sector actually has around 200 bytes in it. So we have some gap, sync ID, more gaps, more syncs, checksums, the payload, another checksum, and another gap. And all this information is so that the control system can properly identify each individual sector on each track, and also determine where the payload is. And using checksums, there's a checksum for the header. What I refer to as a header is all the information the system uses to try and find the payload, and there's also a separate checksum for the payload itself. Now there are a number of sync parts to the sector as well, and there are a number of gaps at the start and end of the sector, and also within the sector. What therefore is to allow time for the system to process the data as it's reading it, and also to carry out what is often referred to as splicing. So if we take a sector and we're going to try and read it, you might find there are variations in the rotational speed of your disk drive. So rather than 2 sectors being butted up against each other, they're separated with some gaps. That allows the system to read one sector, and if it's getting slightly ahead of itself, it can skip or add to the number of bytes in the gap, so it allows the system to adjust the overall speed of reading data from the disks. That brings us to the first complication if you're trying to work on a floppy drive system. If you have a single machine and it has 2 floppy drives, for example, you take one disk and put it into drive A and stream all the data from it, and then you take the same disk on the same machine and put it into drive B, stream all the data, you might find you have slightly different data streams coming off the 2 disks, because the 2 disks will be most likely performing slightly differently, and that can cause some confusion. But the main thing to try and get to grips with floppy drive systems is all this information about single density, double density, this sort of thing, and also the formatting of the disk, because there are certain things that you need to be aware of if you're working on these and you're not familiar with them. Now, the first thing, as I said, is the formatting is entirely up to you, and where you'll see a disk. So I've got an example disk here, and this particular disk says double-sided double density. By the way, sorry if it's dark in here, I'm trying to minimize the flickering on the monitor. But the double-sided double density can be a bit confusing, and there are a lot of variations, so I'll try and skip through this fairly quickly, but it does get quite complicated. But if you kind of understand the basics of it, then it makes the whole thing a lot easier to deal with. So I'll stick to 5¼ inch discs like this one for this discussion, but most of this applies equally to other disk types. So if you have a disk, then the single density, double density and quad density disk media is all the same. There's no difference. It's 300 coercivity magnetic media. And where it says double-sided double density, that really comes down to the way it's been manufactured and or formatted by the manufacturer. But you can take a disk like this, which says double density, and use it in a single density machine. Now, there are some caveats to that, in as much as not all disks are the same in terms of their quality. Some will work better in some drives than others, but the thing to bear in mind is that all things being equal, the media should be the same. The next thing is understanding the difference between double-sided and dual-sided. A dual-sided disk is one that only normally has media on one side of the actual disk. You notice there are 2 read slots in this, and this is for drives like the one we're using here that has 2 read-write heads, one at the top, one at the bottom, so you can put your disk in and the drive can read the top or bottom of the disk without taking the disk out. So that's double-sided. The dual-sided ones are where you would be expected to take the disk out, flip it over and put it back in. And you can identify those normally because they have 2 of these slots. You've got this slot that's for write protect function of the system. So if you cover this up, then the system won't be able to write to the disk. At least not in theory anyway, but again, that's up to you. It's up to your system. But if you flip the disk over, even if it's double-sided, then it's not going to work in a single head drive, because the drive will think the disk is write protected. A lot of people just cut a little notch on the other side, and then most disks like this can be used in a single head drive either way up. You then have another confusion, which is this particular disk says 96 tracks per inch, soft sectored. So you can have soft sectored and hard sectored. With hard sectored disks you have a mark, so this one, if we spin it round far enough, we'll be able to find an index hole, which is there. You can see there's an index hole, but there's only one, so there's a hole that marks the start and end of each track. With hard sectored, you'll have one of these per sector. Hard sectored disks are fairly rare, not used that often these days, or even back in the day they weren't that popular. But some media only supports 48 tracks per inch. This particular one supports 96, even though it's a double density disk. So again, that comes down more to the design of the drive than the disk, and depending on the quality of the media, you might find some disks work well in high density applications and others don't, even though they're all supposed to be the same. So just bear that in mind if you're having a difficult time with some disks. They might just not be that suitable for your drive. So just bear in mind that the physical disk type really comes down to the drive that you're using. Now if you're using high density disks or extended density disks, the media is different. It's 600 coercivity media. That almost certainly will not work in a drive that's meant for this type of media, and vice versa. If you try putting this type of media in one of the more modern drives, then it may well not work reliably. So that's the main thing, is make sure you've got the right type of media for the drive you're trying to use. But just bear in mind, most of the media for single density, double density and quad density is identical. So once you've got the right media type, the next thing is to look at the formatting of the disk. Now the media type and the formatting are two completely different things. The formatting is determined in software or hardware when you format the disk. You can imagine the disk as being completely blank, and even if it's formatted, you can imagine it as being completely blank. You can then reformat it, and what you do to format a disk is you write every single track, but you include all this additional information. So you have to write all that to the disk, and it has to be in a certain format, and it has to be done in a timely fashion to keep up with the drive system, because of course the disk is spinning continuously. If you write all this information to every sector on every track, then of course you have a formatted disk, but what you write is up to you, and there are different formatting styles and variations. An additional complication is you have this single density and double density issue, and as you can probably guess by the name, double density means you write twice as many bits to each track when you format the disk. And the encoding is also different. That's how the density is increased in double density disks. The disk spins at the same speed, and what you do is you encode the data differently. So for single density it's FM encoded, and for double density it's modified FM encoded, and the two are completely incompatible. You can't read an FM encoded disk in a modified FM mode. Most systems will support both, but you need to switch to the correct one. But once again, that has nothing to do with the actual formatting. That's just the way in which the bits are encoded on the disk. So like I said, to format the disk, you just write down, you write all the tracks onto the disk in whatever format you want, using the encoding that you want. But you have to decide the sector size you want to use and how many sectors per track. Now, because the disk is spinning at a constant speed, you have a finite number of bits for each full revolution of the disk. It doesn't matter whether you're at the outside of the disk or the inside of the disk, the number of bits per revolution is the same. So what you have to do is figure out how many bits in total are in your sector, including all the gaps and the sync and the ID and everything, and the payload of course, and then you divide the number of bits on the track by that number of bits in your sector, and that will give you a number that you round down, and that's the maximum number of sectors you can write. And that's really determined by the rate of rotation of the disk and the frequency of the clock you're using to write the data onto the disk. So the next question is, well, why have we got different size sectors? Why not just pick one? And the reason really, it comes down to efficiency and performance. So let's say you've got a file that's 300 bytes long. If you try and save it in chunks into 128 byte sectors, you're going to lose maybe 50 bytes, something like that. Whereas if you have a 1024 byte sector, you're going to lose 700 and odd bytes when you try and save that file, because once you start using a sector for a particular file, you effectively earmark the entire sector. You use one or more sectors, but once you've started writing bytes into the last sector in your set, then you effectively occupy the entire sector. So even if you only write 1 byte into the sector, you've basically taken up the entire sector. But in a 128 byte sector formatting, the most you'll ever waste is 127 bytes. In a 1024 sector formatted disk, if you write 1 byte to the sector, you lose over 1,000 bytes. The advantage in the bigger sector sizes is it cuts down the amount of overheads. So for this small 128 byte sector format, we're losing very nearly half of the disk space with the headers, because there are so many headers. Whereas if we go to bigger payload sizes, the header information is the same, so the headers are the same size, but the payload is bigger. So we lose less of the disk to the header information and we gain payload, but we may well lose the payload if we're only writing small files to the disk. So it really comes down to what the system is going to be used for as to which one you prefer. So that said, I've been testing this particular system using different sized sectors. I've tried quite a number of different drives just to try and make sure that the system is reliable. So what I will do now is just demonstrate the system running. I've got a floppy disk in the drive. We've got our interface connected. This is still the version 3 of the JMZ board, although I now have version 4, which I'll be swapping over to fairly soon, and they seem to work fairly well. A few additions to that. But this floppy drive interface will be on the next version of the board. I've not yet implemented DMA into this system, so I'm using programmed in-out to access this interface. It's quite difficult at the moment because I'm still running the board at 2.5 megahertz, and that's really pushing the limits as to being able to read a floppy disk in code rather than using DMA. But effectively what we do is we write bytes directly to the floppy drive controller. It then writes all the bytes to the disk, and we have to make sure that we're writing the correct bytes, as I've just been talking about, when we format the disk. So the program I have loaded at the moment into the computer is a fairly simple program. We'll look at the code in a few minutes, but it's going to try and format this floppy disk, and there's also a block in the program that allows us to read the disk back. I'll just move the camera across a bit so you can see the scope. So you won't be able to see the floppy disk, but you should be able to hear it. It's quite an old one, it's quite noisy. And also I'm stepping it at quite a low rate for this testing, so it tends to be quite loud. And what we have on the scope is the yellow trace is the DRQ line coming from the floppy drive controller. The purple is the write line going to the controller that comes from the Z80, so every time we write a byte we get a low going pulse on that line. And the green trace is the index signal coming from the drive. It's not running at the moment, that's just showing what I captured when it last ran. So we'll start the program running, and this is going to try to format the floppy disk. So you can see the data that's been transferred on the scope, and on the screen hopefully you can see we've got the formatting information. So I'm formatting this to 35 tracks, and the status information is just the error code or the status code returned from the floppy drive controller. The number's counting in hex, so it's going to go up to 22, and then it should stop. And then we'll try reading the disk and see if the formatting has been successful. Okay, and we'll try reading that back. We're going to try reading track 0 sector 9, that's what's coded in the program at the moment. We'll try changing that in a minute and reading a different sector. All the sectors should be formatted. I should point out here that rather than putting in just the general filler information in the payload, I've actually put some text in there so I can make sure that we're not just repeating the same bytes. So we should see some text appear on the screen when we try and read the sector, and it will show hopefully 128 bytes of text. And as you can see, that's exactly what it's done. So I'll just make a small modification to the program to select a different sector. So that value 9 is the sector number. We'll change it to 3, for example, and then the error is just the way we get out of the monitor edit mode. So now we'll try reading that sector. The LEDs are just indicating the hardware status. So as you can see, it's working fine. We've managed to successfully format a disk, and we can read back the information. So what we'll do now is go and have a quick look at the program that the Z80 is running. It's still very basic. This is simply for testing, so there's no bells and whistles on it really. It's just to get this interface working, get the design working, and then I can write some proper BIOS routines for CPM. Okay, this is the code that we're currently running on the Z80. It's fairly straightforward, and as ever I've configured this so that I can send it through the RS-232 port, and it makes it very easy to debug and to test. So the first thing we have is some equates that allow me to just define the various commands and whatever. I'm using a TMS2797 as the floppy drive controller, but also we need some additional bits to control the side of the disk, for example, and which particular disk we are selecting. So there is an additional port, but rather than using multiple ports to access the interface, I've mapped the ports, as you can see here, in a particular way all through port 5. So these are all port 5 in-out addresses. So we've got one port 5 in port that we're using and one port 5 out that we're using. Okay, so we also have the commands, and I'm also testing this particular interface with a TMS2791. The only real difference between the two is the data bus is inverted for the 2791, so we also have to invert all the bits in the commands. Okay, so we have the usual data bytes for the system to start up. Now it's running under the monitor, so the monitor is running on the Z80, so we don't need to set up a stack or anything like that. We can just use the ones or the one that's been set up by the monitor itself. But we do need some bytes for showing the text, etc., that you saw on the screen, and also some values to store in RAM for the various variables we're using in the program. So this next block of data is the information that we have to send through for each sector that we're formatting. So you can see there's a lot of information, so the only part of it that's really the payload would normally be this bit, and this is kind of dummy data that you write into the payload when you format. What I'm actually doing in this program is using this information, and this is the disk, that the text that you saw from the disk on the screen. And this is just so that I can make sure that we are actually formatting the disk and not just reading data that's already on there. So this is commented out, but even so, you can see there's a lot of information here, and this is the only part that's data. Everything else is part of the header and the gaps, checksum, everything else, and we have to do this for every single sector on each track. So you can see there's a lot of overhead. The only bit that you normally get from the floppy drive controller when you try and read a sector is the actual payload. It doesn't normally return the rest of the data. That's just so that it can figure out what's going on. And it also makes it confusing when you don't get data back. It looks like the system's not working, but it may just be the track or side or sector or the checksum is wrong and doesn't match what you've told the system you're looking for. Now, you wouldn't normally encode it like this in a program. It's very inefficient. What you'd normally do is just encode it like this. This is how I'd normally do it, kind of run length encoding. So this is, I want 28 hex bytes at FF, 6 bytes 0, so it's quite an efficient way of packing all this into an easy to use format. So when we start the program, it clears the video, prints the welcome text at the top, loads some values into the variables that we've set up. So although they are set up when we compile the program, we might be re-entering this. We need to make sure they're set each time we start the program. We then write all this information into RAM, so that that's for each sector, and that's so that we can very efficiently send that data through to the drive as it's requested by the drive controller. We then get to the format loop itself. Quite straightforward. We write the information that we saw, that's the sector number, etc., onto the screen. We wait for the floppy drive controller. Now this gets a bit difficult to follow if you're not familiar with the controllers, because you need to include certain delays, because the controller works in a bit of an odd fashion in some ways. And internally, if you write to this register, you need to wait for a while before you can then read back what's going on. And if you don't do that, you'll end up reading back the wrong information. So you need to wait. You see there's various delays here, so you need to wait for the floppy drive controller to respond. You also need to wait for the drive itself to be prepared. So when you load the head, for example, you can't just immediately start trying to read or write data. There is a delay built into the floppy drive controller, but it's nowhere near long enough for these old drives. And if you try reading or writing data immediately, you'll probably find the first few sectors are just full of rubbish. Once we've made sure the floppy drive controller is ready, we then have to load the HL with the start of the buffer that we've established with all the data in it, and that's so that we can use HL as a pointer to very quickly get the next byte from RAM. We then load the track and sector registers for the beginning of the disk, and this is the point where we start actually formatting, and we're going to write a track. In fact, we're going to repeatedly write tracks, but we start with the write track command. We load that into the floppy drive controller control register. We have to wait a short time. As I said, if we try reading the status immediately, we'll get the wrong value back. And what we do then is we wait until the floppy drive controller requests a data byte. Once it's done that, we send the data byte through to the floppy drive controller. It will then write that to the disk. We wait for the DRQ line to go back low again, indicating that the floppy drive controller has received the byte. We jump back to the start of this loop, and we keep going round until the task is finished, at which time the busy line will go low. And when it does that, we jump through to the format done. Format's not completed yet. This is just one track. So we then update a few variables, we jump back to the start of the format loop, and we do it all again. And we do that for as many tracks as are on the disk. And once we've finished, we get down to this finished formatting. We wait for a short time, we home the drive to get the drive back to its track 0 position, print out any errors that may have occurred, clear any interrupt that may have occurred while we were tidying up, and then effectively we're finished. We return, and that's the disk hopefully formatted. The bulk of the remainder on the program is just for writing the text to the screen, the delays, apart from the bit at the end, which is the read section. So to read the disk back, we clear the video. In this case, when we read the disk, all it's doing is writing the data as it comes from the disk directly to screen RAM, which is why we can see the text. And it just goes around, starts the read read sector command, and it just keeps reading bytes and putting them on the screen until the entire sector is read, and then it returns. So as you can see, very straightforward, very simple, and it does seem to be working well. It's just really getting the formatting sorted out and getting the timing right. This still needs a few additions. So for example, I need to still synchronize the start of the process with an index mark on the disk to make sure the two don't clash. It's fairly unlikely they would, but just on the off chance, if that occurs, the formatting will fail. Other than that, this is almost complete, and this is the sort of, apart from the text out, which you probably wouldn't use in this context, this could now go into a program that you could load from your floppy disk when you're running CPM. So as you can see, we're making good progress. We'll go back to the computer and try this one more time. So back at the computer, I'll move the camera across. You can see the floppy disk. So we'll run the floppy disk format command again. The LEDs on the interface, the one on the right, or the two on the right, are for the drive select. So the one on the far right is drive 0, and the next one along that's not illuminated is drive 1, and the third LED is the density select line. So I was currently selecting a single density. Okay, so that's finished formatting. We'll try and read it back one more time. And as you can see, that's working just fine. So, as I say, the interface for the floppy drive is coming along nicely. It does work well with both drives plugged in. I can select either one and format and read from both. And this circuit will almost certainly make it into the next version of the board. And once we've got access to the floppy drives, then it makes it much easier to start sorting out the BIOS, etc. for CPM. And once I've got CPM running, I will most likely go on and write my own operating system. So a lot of fun doing this sort of thing, and hopefully you found this of some interest.